All right, maybe we should get started. Yeah. All right, so welcome to another class of CS 545, the introduction to robotics. So today we'll be covering Bayesian networks, part 2, because we covered part 1 on Monday. So a few logistical things. So lab 1 is due February 4th. Hopefully you have made some progress on that. And I mean, I showed you what to expect from the turtle sim last class, so hopefully you were able to do that. If not, you could just watch the video recording and then try to get something similar. Yeah. And again, the lab 1 is mainly meant to make sure that you can actually run ROS and like submit things and run things, and then you'll build upon it for subsequent labs. So I saw on Piazza that a few of you wrote your team and you posted there today. If you don't have a team right now, then it's getting very late. So try to find a team. If you can't get it done by today, maybe try to contact the course staff and we can try our best to help out. But try to make sure you have a lab by today. Yeah, and you have some nice lab names. I saw some of the names on Piazza. I think for a few of you, I had to suggest revision to your team name. So if I ask you to change your team name, to take a look at that comment. Yeah, and we are working on grading homework 1. We will get that to you soon. And yeah, just keep an eye out if we need more information from you. But I think we'll try to get it done in a few days. And then you can see the grade on Gradescope. And homework 2 will be released maybe early next week, and then you'll get another 2 weeks to work on that. Yeah, and I thought, yeah, I skimmed your homework 1 to look pretty good. We're not going to be too strict about the 1 page per question. So I know some of you were a little bit frustrated by that. So, if you need a little more, that's okay. Any logistical question? And again, I have the Google Doc open, so if you prefer to type it in, you can do that. So I know some students prefer that. Yeah. All right. Any question? All right. There's no question, so I guess we'll just move on to the technical portion for today. So let's recap a little bit of our probability. So in the last few classes, we talked about conditional probability. So if we have random variables x and y, the conditional probability of x given y is just their total joint probability divided by the probability of just y. So intuitively, it's like whenever you have y, you just, in the numerator, you take all instances of when this y happened, and then you also compute whenever this x happens. So this notation, again, is short for probability of random variable x taking on value little x. And then given that the random variable y takes on the value small y. So we just write that in the shorthand notation. So it makes our life easier when we write things out. So we covered the product rule where this is true for any joint probability with 2 random variables. Anytime you have probability of x and y like this, you can always factorize it like probability of x given y times probability of y. And you can also do the same thing if you happen to reverse things. So if you prefer doing probability of y given x, you just change this to be probability of x. And this is a simplified special case of the chain rule where it generalizes. So if you have n total random variables, then your probability of the joint would factorize as follows. So you have probability of x1 times probability of x2 given x1 times probability of x3 given x1 and x2. So you have to make sure that you keep all of the preceding random variable when you factorize it like this. Yeah. So again, the product rule and the chain rule conditional probability, they're always true. But today we'll see like when we can simplify those assumptions. Or simplify those rules based on assumptions of our data. Yeah. And X and Y are independent if and only if the following holds. So you can imagine you look at a table, go through all values of X and Y and make sure that the table for the joint and the table for all the marginal, they work out to make sure that this equality is true for all X and Y. So if they're discrete, you have to check all of their values. Yeah, and same thing for continuous too. Yeah, then X and Y are conditionally independent given Z if and only if this holds. So for any X, Y, Z, this thing should factorize into this. So it's the same thing as the independence here, except you just condition on Z for all the terms. And you can generalize it. So Z can be like a tuple of Z1, Z2, Z3. So you effectively can condition on as many things as you want. As long as you're consistent, you have to condition here and here and here for all the terms. And the shorthand that we might use, at least for this class, we'll be using is X is conditionally independent of Y given Z. So you'll see this a lot throughout today. And last class, we also talked about Bayes nets. So a Bayes net, that's short for a Bayesian network. Another way to call them is graphical model. So they're an efficient encoding of a probabilistic model of a domain. So we have some domain, and we're going to try to model it. So we have to make simplifying assumptions. We're going to include variables for things that we care about, and then for something, we're just going to decide that they don't belong in our Bayes net. So you remember that this was the Bayes net of like the car accident, or like the factors that might lead to, car accident, medical costs, liability, or basically insurance. Yeah. Yeah. So again, I think you can do, things like inference. So given this Bayes net, what is the probability of X given E? So E is short for evidence. So you can think of E as like a set of arbitrarily long, random variables and an assignment to their value. So you might ask, what is the, I guess, yeah, what is the probability of an accident given evidence from someone's age and someone's driving skills? So presumably, age somehow affects some of these other factors, like age affects whether you're a good student or not. So I guess maybe the younger you are, the better student you might be. And then the better student you might be, then maybe it will propagate to being, at lower risk for an accident. Yeah. So most of you, I think, would be the good student category. And yeah, sometimes you'll see Bayes nets that are shaded. So whenever you see the shaded thing, usually that means these variables are observed, so they're like evidence, and then the ones that are like not shaded in, they're unknown. So they might be the X, the thing that you care about, or maybe there are other things and you have to like marginalize them out when you compute the probability. And today we'll be talking a lot about question related to representation and modeling. So given a Bayes net, what kind of distribution can we encode? And also, what Bayes net is most appropriate for a given domain. So you might have two different Bayes nets that could encode the same distribution. So which one do you pick? So we'll be talking about that today. Yeah. And again, I think we also talked about this last time, but just to review for some of the semantics of how BayesNet works. So they're a directed acyclic graph. So you'll see like this cartoon, just think of these circles. I don't know what this actually is, but it's like some kind of sphere, and then you have arrows pointing from one to another. And that forms a directed acyclic graph. And each of these nodes is a random variable. And they will have each a conditional probability table. So what that means is for each node here, it has a collection of distributions over X, one for each combination of the parent value. So that's what we mean here. So probability of X given some assignment to the parent value. So A1 all the way to AN, those are like explicit assignment to the value of the parent. So if the parents are all discrete random variable, you should say, random variable A1 is equal to lowercase a1, random variable AN is equal to lowercase an, stuff like that. And then X here, we keep it as capital because it's like a random variable that could take on different values. So this whole expression here refers to a table with like the number of rows equal to the number of values that X can take on. And the BayesNet will implicitly encode joint distribution. So they do that as a product of local conditional distribution. So a key advantage is that you can have a huge graph like the one that we showed here, but you can analyze it and make queries by just analyzing small subsets of the graph based on the structure of where the arrows are. Yeah. And this is the definition of the joint when you make the assumption from a Bayesian network. So you have probability of the joint. If we didn't make any assumption, if we didn't know anything about the Bayesian network, we would have to say, xi given all the preceding values of the random variable. But we can just say, let's just look at the parent. And if the number of parents is very small, like 1 or 2, then you get a huge amount of saving from this. And by savings, I mean, when you encode probability table, you have to use some amount of data, like the more rows that you have, the more data you have to take up. So using fewer rows makes it a little bit easier to analyze. Yeah. Any question before we move on to some examples? Yeah.
The conditional probability table is from the statics data or just the calculated data?
So are you asking if you have a conditional probability table, how do you get the numbers in there? Well, you can get that from data, like maybe you have a data set and then you can compute the probabilities and then you can just put them in there. Or you might be given some distribution that someone else computed. Usually that's going to be the case for this class, like we'll give you a distribution. So you don't have to worry about, putting in how to get the number. But in practice, what you might do is you might analyze some data in a domain and then you have to like compute the probability by just, adding up the numbers and then computing probability that this equals that given the parent and stuff like that. So you would have to do the work if you're starting from scratch. Yeah. But for here, we're just going to assume that we'll give you table, at least for this lecture. But yeah, this is just a table that we'll just give you the numbers. So this is an example Bayesian network with the random variable, the BEAJM. So this is like an alarm network example where B is whether or not a burglary occurred or not. And, A is like whether or not the alarm went off, and E is like whether an earthquake happened or not, and then J and M are like whether or not your neighbor calls you, or how do people communicate these days? Do you like I don't think people use normal phone calls anymore. So just imagine that they represent some binary random variables that say, this person, John, contacts you. So, and all of these are binary. So if you want to know how to read these tables, just look at like B and then you get plus B. That means B occurred, and then minus B is B didn't occur. And same thing for the others. So maybe just take a quick moment, and if you're given this joint probability, then how would you factor it? You don't have to like actually compute the numbers. You can just write out the conditional and then put in the numbers from the table, and then you'll get like some amount of numbers multiplied by each other. Uh, yeah, and if you've already downloaded the slide, then try not to look ahead. Yeah. And while you're thinking about that, here's another question just to make sure you understand the table. So if you look at the table with A and J and probability of J given A, then why do the numbers here not sum to one? Like there's four numbers, but they don't sum to one. Like why is that? Why did my mouse keep disappearing? It's like, yeah, that thing. So it doesn't sum to one. Why? Yeah.
So like the first and the second 0.9 and 0.1, that would sum to one, and then 0.05 and 0.95, those would sum to one. But it's actually two separate distributions, so you can't expect all of them to be summing to one.
Yeah. So yeah, there are two separate distributions in that table. So you remember that every assignment of the parent define a distribution. So you have to, because you're conditioning on A here, you have to pick one assignment of the A, whether it's plus A or minus A. And then that defines a valid probability distribution if you sum over all the numbers, both of the numbers here. All right, now, it's kind of hard to see, but I'm trying to highlight each row that matters for this. But if you went through the computation, you should get something that looks like this. So you get this joint that factors into probability of plus B, because B has no parent, so you can just do your probability of B given the parent, but you have no parent, so then just write probability of plus B, and then you get same thing for probability of minus E. And then you get probability of A plus A given plus B and minus E. Probability of minus J given plus A. Probability of plus M given plus A. And I see someone got it in the Google Doc too. Yeah. And yeah, I don't know what the value of that multiplied to, but like this is the main idea. Just understand how to get from the joint into the conditional. All right. So let's talk about the size of a Bayes net. how big is a joint distribution over n Boolean variable? So by this, we're talking about like, what is the size of a table that you might have to make that enumerate all the possible combinations of the n random variable? Yeah, so how big is it? Yeah, so it's 2 to the n. Everyone gets why this is true. So for every, no, we have n variables, each of them has 2 combinations, and then you have to write out all of the combinations, it's 2 to the n. Yeah. So what about a Bayes net if the nodes have up to k parents? So what would be the size of that? I'll let you think about it for a few seconds. Yeah, so here you can argue that the size is O of, no, that's big O notation and like, computer algorithms and stuff. So it's on the order of n times 2 to the k plus 1 power. So the reasoning is you have n nodes in the Bayes net, and for each of those, for each specific node, you could have up to k parent. So that means for a given node that had like 3 parents, and if they're all Boolean, then you get 2 combinations for, 2 choices for the first, 2 choices for the second, 2 choices for the third. So that's 2 to the k, and then you have 2 choices for the current variable, which adds another power of 2. If you choose to represent, if you choose to represent both of the values of your current random variable. Is that clear on? I can write out the table if you want. Yeah.
I see tables.
Yeah. So here. I'm just trying to make sure that the recording can capture some of what's here. So let's suppose there's a node with 2 parents, and then. Oh yeah. If we're doing like Boolean random variables, just think of it as like heads and tails. So you have tail, 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 or just true and false. Yeah, yeah. True and false or whatever. Yeah, so what I try to do is I try to write out all the possible combinations here, and then we're really taking x3 and conditioning on x1 and x2. So there's 8 numbers here, but it's really because, yeah. So for each combination here, we have 2 values of x3. But if you knew that they were Boolean, you can also just eliminate one of those rows, and then you just know that it's 1 minus, this probability. So you don't need 2 to the k plus 1, but if you really want to represent these explicitly, you can do that. And then because there's k, k equals 2 here, and then 2 to the third and 8 for that. Yeah. Yeah.
One random word B is a question refers to the size of the network actually, or the number of the rows in the conditional probability table.
Oh, so you mean like when you're talking about how big it is, like what did that really mean? Like how it means basically the size of the joint probability table when you have to write out every possible combination. I guess really what I should say is for each of these rows, there's some probability. Like you can get 0.6, 0.4, then you can have different numbers for the different distribution. Hi. So when you have your normal joint distribution versus your Bayes net, both of them give you the power to calculate the joint, but the Bayes net benefit is supposed to give is that it gives you a lot of savings in terms of space when you try to write out the full table. And it's also makes it a little bit easier to analyze like local conditional probability tables, as well as it can make it faster to answer query, which we will talk about soon. All right, so we're going to talk more about conditional independence. So remember again that x and y are independent if for every possible value of x and y, this thing is true. And then you have conditional independence if the same thing, if it's like this, but with conditioning on the same thing, like conditioning on v here. And so if you remember the example from last class, we might think that, alarm is conditionally independent of fire given the smoke. Now, normally, alarm should not be independent of fire because your alarm should go off when there's a fire. So they're heavily correlated. So if they were independent, then knowing one would give you no information about the other thing. But if you know that there is an alarm, it probably gives you a good hint that there's fire. But the key is that if you condition on smoke, maybe the smoke explains all of the connection between them. And so once you know that, it doesn't matter like whether the alarm is true or not, it gives you no information about fire, conditioned on smoke. All right. So one thing that we've already assumed about Bayes net is that when we're given that graph, you can make the assumption that the joint distribution factorizes into the probability of each node given the parent instead of probability of each node given all the preceding nodes. But there are other assumptions that you can make based on the structure of the Bayes net. And you can read them from a graph. Like if we give you a graph, then you can make a conclusion that this random variable must be conditionally independent of this other random variable. And when we choose to model some data or some domain, then it's very important to understand the assumptions that are made when choosing a Bayes net. But a general principle is you want your Bayes net to encode, just enough assumptions that match the domain of interest, but you don't necessarily want to, make a Bayes net that has, like I guess too few assumptions or maybe has too many assumptions. So you just want to have like the right balance, and we'll talk about that, I believe, right now. Yeah. All right, so here's an example. So everyone knows how to write out the joint probability. Like if I ask you probability of x, y, z, w, the joint probability, how do you factorize this? And when you do factorize it, can you also think about what are the additional implied conditional independence assumptions? So I guess we're looking for statements of the form, this is conditionally independent of this given this third thing. I'll give you a couple seconds to think about this. So yeah, I see something in the Google Doc with a distribution, but whoever wrote it, you can simplify the last term. Yeah. All right, so everyone wrote out the joint probability of this, right? So you can write it out like this. So probability of X, Y, Z, W, you factor it in terms of this thing. So the only thing you need to do is, probability of this thing conditioned on whatever its parents are. So X, it doesn't have any, so it's just by itself, but then these are just conditioned on one other thing. So when you see this distribution, what are some examples of conditional independence assumptions that are guaranteed from the structure of this graph? Like, for example, are we guaranteed if we see that X is independent of Y? Are we guaranteed that? Yes or no? Yeah, so when you see the structure, you have X is like pointing to Y. So you can have random variable Y be defined as like Y equals X, okay? And then in that case, they're not independent. They're clearly not independent. They're very correlated with each other. So when you see this thing, you cannot guarantee that X is independent of Y. They might be for some particular instantiation of your distribution here, but it wouldn't make sense if you had an arrow going from X to Y. Because if you remember from last class, you can kind of think of the arrow as representing a causation or causality. Like X might cause Y, which might cause Z, and so on. But you can make some assumptions here. So the assumptions that you can make here are Z is conditionally independent of X given Y. Yeah, so Z is conditionally independent of X given Y. Yeah, do you see why that might be true intuitively? If you think that X causes Y, which causes Z, but there's no arrow that connects X and Z, right? So the only arrow is from Y to Z. So if you know Y, you'll know Z. Or I guess if you know Y, it'll affect your knowledge of Z. That's the more precise term of way of saying it. And there's also other guaranteed conditional independence assumptions. And yeah, we'll talk about how to derive all these pretty soon. All right. So in a Bayes net, if you are asking whether two nodes are independent, given some amount of evidence, if they are truly independent, then you can try to use algebra and like go through all the possible combinations of X and Y, or if X and Y are your random variables here, you can like go through all their possible combinations. If they're not independent, you could just prove the counterexample by like going through the probability table and finding values that don't make the independence definition work out. So if you look at this chain, are X and Z necessarily independent, or are they guaranteed to be independent if we give you that structure? So it's similar to the question that I gave last slide. Yeah. So is this true? Are they guaranteed to be independent? Anyone? Oh, yeah. Well, you're not given one. It's just X and Z. Yeah, so because you can have X, which causes Y, which causes Z. So if you know X, then it probably gives you a hint, or it changes the knowledge of the probability of Z. But no, they could be independent. So this is something important to see. The question here is, are they necessarily independent? That means, are they guaranteed to be independent no matter what distribution, what numbers in the probability table you might have? So you can try to tweak all the numbers to make them different. You get different distribution, but this question is asking, no matter how many values you try, are they going to be independent? And the answer is no. So you can easily make tables or get numbers that cause the independence definition to fail. But they could be independent depending on the numbers that you put in the table. So you can make X, Y, and Z be independent events, like independent coin flip. But in that case, it doesn't make sense to use this as your Bayes net. It's not, it's a valid Bayes net, but it's not a good match for the problem that you're considering. So that's the nuance here. Like, you can answer questions about, like, are they guaranteed to be independent given the structure? But you can't say things, but even if you have that, it might still be, independent sometimes. So. Okay, so, all right, so I see a question in the Google Docs. So on slide 12, X was independent. All right, so so I guess the question is, X was independent, right? That's not a valid question, because to say that, you have to say like two things are independent. You can't just have one thing. So you need to have at least two random variables to do a test of, are they independent of each other? Yeah. All right, so I see another question. So if you're asking about X and Y, the way to think about this is X and Y are not guaranteed to be independent, because this thing can model something that a causal chain. X is something like pressure in the atmosphere. Y is like the event that is raining. So X would cause Y, but you might get some numbers in the probability table such that if you go through the definition of independent, it actually satisfies independence. But in that case, you can still use this Bayes net. It's a valid Bayes net. It just doesn't make sense for the problem domain that you have. So that's the nuance we're thinking about independence in Bayes net. We're going to go through more examples of this. So yeah. So yeah, just think of it like this. So, they could be independent if we make our distribution be a strange one, like, X, Y, and Z really are independent thing, but yeah, it's just not a good match for the Bayes net. And that brings us to D-separation. So D-separation helps us to study independent properties for triples of nodes, which we can then use when we analyze a bigger Bayes net with like more than 3 nodes. And when you look at 3 nodes in a Bayes net, like, you'll see that we cover the possible combination of how 3 nodes could be connected to each other. Then you can use rules to analyze, are these variables like guaranteed to be independent of these others, potentially conditioned on some evidence. And yeah, D-separation is this algorithm for like answering queries like that, like what I just said. All right, so a causal chain. So we have seen some examples of that, but let's just make it a little more concrete. So X is low pressure, Y is rain, and Z is traffic. So in your domain that you're modeling, you might decide these are the 3 random variables that you care about. And if that's the way that your Bayes net is structured, remember that Z only had Y as the parent. So it doesn't have X. So you can factorize your joint distribution like this. Yeah. So that's just using the chain rule, then you remove like X from the probability of Z given Y. So going back to something we already covered, so X is independent of Z. We are not guaranteed that. And the way that you can show that is you just need like one example of conditional probability table for which X is not independent of Z. Right. So the example here is if you have these numbers, then you're not going to satisfy the rule for independence. So going through this slowly, it says if we know that there's low pressure, the probability of rain is 1. If we know that low pressure is not true, the probability of no rain is 1. So like, and then if you have if you know plus Y is true, then you automatically know plus Z is true. And same thing if you negate this. So what these numbers are saying is that if you know X, you're guaranteed to know what Y is, and then you're guaranteed to know what Z is. So there's no way that X and Z can be independent. Because the whole point of independence is if you know something about one thing, it doesn't tell you anything about the other. But if you use these probabilities, once you know like X, you automatically know Z. Yeah. So that's why they're not guaranteed to be independent. What about X is independent of Z given Y? Is that guaranteed? I mean, if I say no in the first slide, then I give you the next slide, you kind of know that the answer changed, right? Yeah. So this is the definition of the conditional independence, where definition of conditional probability, sorry, where you have this, and then this is just the definition. And if you factorize the numerator, you get probability of X times probability of Y given X times probability of Z given Y. Now you don't have given X, right? Because you can eliminate that because Z only had Y as the parent. And then just remove the common factors, and then you get this thing. Yeah. Yeah. Everything clear about the causal chain? Yeah. So I guess one intuition is that you can kind of think that evidence along the chain, which means you observe something, it blocks the influence from, proceeding in the chain. So you see Y, then that tells you all you need to know about like, Z. So you don't need to, knowing X doesn't help. All right. So we talked about the causal chain. So that means 3 nodes, like connected to each other in a sequence. This is a common cause. So you have 3 random variables. Y is your project is due. Or we don't have projects in this class, we have labs. So just say your lab is due. Then Piazza is busy, right? Okay. And the lab is full. This is going to assume you're in like lab 3 and 4, where you're going to be there in person. Yeah. So what do you think of this? Like, if your project is due, what's going to happen? So are we guaranteed that X is independent of Z here? Piazza busy and lab full. They don't seem like they're independent because they seem correlated. Like if I see that Piazza is very busy, I might think, oh, the lab is probably busy and vice versa. And same thing here, you just need to show one example of conditional probability table for which the independent definition does not hold true. Yeah. So if your project is due soon, then Piazza is probably busy with probability 1, and the lab is full with probability 1. So if you look at the numbers and you see that plus X is true, you automatically know plus Z is true. So they cannot be independent, because if you know one of them, you automatically know the other. And again, the whole point of independence with two random variables is that if you know one random variable, it doesn't help you with your knowledge of the other random variable. Yeah. All right. So if you know the pattern of this, then the next slide is going to show, are we guaranteed that something is conditionally independent of something? And if the answer is probably going to be yes, because I said no here, then the next slide is going to say yes. So what is guaranteed from the structure? Yeah. So can you say that statement, please?
Depending on Y, Z is dependent
No, I'm looking for a statement of the form, this is conditionally independent of this given this.
on X is conditionally dependent on Z.
All right. So this. Right? So if you do the calculation here, and again, use the definition of the conditional probability here, then you simplify it by making use of the Bayesian assumption, then yeah, you get this. So the intuition here is, if you observe the common cause, if you know that the project is due, then that'll block the effects, or block the influence between the effects. So in other words, like if I know that the project is due, like that already, like knowing that is like enough to explain the correlation. So at this point, if I know the project is due, and I know that Piazza is busy, that doesn't give me any more information about whether the lab is full or not, because I already know that the lab is like probably full from the project. So if this is true, like, it just doesn't give me any extra information. Again, this is an assumption made from the structure of this common cause. So again, you might think, well, maybe there should be some influence there. In that case, you should not use this Bayes net. You should use a different Bayes net that satisfies your assumption of the variable at hand. All right, this is the most interesting one. So you have two nodes that both point to something else. So maybe X is raining, Y is ball game. What ball game do you prefer? Like baseball or basketball or cricket? Is that I don't know. Then Z is traffic. So what happens here? Are X and Y independent? Yeah. So yeah, the ball game and the rain, they might cause traffic, but they're not correlated. So there's no like direct arrow from one to another, then there's no like common effect here. So if you want to kind of show it mathematically, you could try including all the random variables here, like probability of X and Y is the same as this thing. So you add in Z, but you marginalize it out. So this is just the definition of like, marginalization. This is the chain rule. And then what I'm doing here is I'm moving all the terms that don't depend on Z, the sum, outside of the sum. And then here we have like the sum over Z, but this, for a given value of X and Y, this just sums to 1 because it's a probability distribution. So by definition, it must sum to 1. And then here you condition on X, but X is not a parent of Y, so it doesn't belong there by assumption of a Bayes-Nash structure. Are X and Y independent given Z? Are we guaranteed that this is true by the structure of the Bayes net? I think I see different opinions in somewhere. So no, so they're not guaranteed to be independent given Z. So the reason is, if you know that Z is true, then that puts these two random variables, X and Y, they're kind of like in competition to see which one causes the other. So if you know, if you observe Z and you know that it's raining, if you know that it's raining, that actually means the ball game is probably less likely because Z was X was the thing that caused Z. So if you know one of them, it decreases the probability of the other one. And that means they're not independent because the point of independence is if I know something from one random variable, it doesn't tell me anything about the other one. Yeah. Yeah, so that's why I think this case is a little bit trickier to think about compared to the other two because observing an effect activates influence between the possible causes. So yeah. So it just takes a little bit more, a little more thinking about this case when you're trying to analyze which conditional independence or which independence assumption hold for a given Bayes net. And so we talked about 3 special cases with 3 nodes, but most Bayes nets will have many more nodes, or they'll have like many different types of structures in them. So the interesting question is, in any given Bayes net, can we claim that 2 random variables are guaranteed to be independent, possibly given some evidence? And if you analyze the graph, any example can be broken into different repetitions of the 3 canonical cases that we just talked about, like the common cause, the common effect, and then the causality. So how do we do this? Like, one way that you could try to do this is to just look at a Bayes net, shade in any evidence node, and then look for any path in the resulting graph. And if any 2 nodes are not connected by an undirected path, not blocked by a shaded node, then they're conditionally independent. Yeah. Maybe let me draw this out. It's a little bit, I don't have a shade, so let me try to draw this out here. Oh. R given B. All right. So is L independent of B given R? So what I might do is I might shade this node, and then I look at L and B. So here's L and here's B. And so the answer is they are guaranteed, like this independence assumption is guaranteed to be true because this is like a causal chain. You have like L going to R going to T, and then R blocks the influence. So if I try to go here, it blocks the. But now with L independent of B given T. So if we shade this, then what happens? Then if you have a path from, say, like, if you have a path going from here to here, then you might think that yeah, is L independent of B given T, then what happens here is that T is like T like activates the connection here. So if you like know L, then it decreases the problem. If you know that L is something, then that changes your knowledge of B. And the same thing, if you know B, it changes the knowledge of L because of this common effect that happens. So that's where I think this is like the tricky case that requires a little bit of thinking when you're working with the Bayes net. Yeah. So yeah, if you have any kind of B structure like this, like R, T, and V, it doesn't count as a link unless it's active. By active, I mean activate by observing T. So this is a little more the more formal way to do it, and this is like the correct way to do it. If the question is, are X and Y conditionally independent given evidence variable V? Then the answer is, well, yes, if X and Y are D-separated by Z. Yeah. So the way to think about this is consider all the paths undirected. So don't worry about the direction of the arrow. Just think of like any undirected path from X to Y. If there's no like active path between them, then they're guaranteed to be independent. Yeah. So a path is active if each triple is active. So, you have active triples here, like, this node, and this node, and this node, they're like, an active path. So you can't claim that, they're like there exists. All right, so in other words, there exists an active path. Therefore, they are not guaranteed to be independent. And so we've seen these examples before, but this is like trying to put everything in one slide. And the other thing I'll mention is that this last case seemed a little bit tricky, but just think of this active thing as something like, just think of this as something that's like measure this thing. So we used some examples of, I think we used some examples of, well, what was it that we used here? Oh, traffic. So you can think of this as traffic. And then this other thing is something that measures traffic. So like a sensor that tries to deduce what is the traffic level from traffic. And then if you know that, then that activates the connection between these two nodes. Yeah. So knowing one of those will affect your knowledge of the other one. Yeah. And so if you have any single inactive segment, then you block your path. So any questions on this? Because this is like probably the most important slide to understand today. Yeah. Yeah. And if there's no question, we'll probably take like a 5-minute break right now. Then I'll just let you look at this slide because it's so important. Yeah. Yeah, so anyway, let's take a 5 minute break. We'll go back, we'll come back at like 5:05, and yeah, if you need a break or whatever, just, get some water or whatever, feel free to go ahead, yeah. I mean, there's some, yeah, so what this is asking, this is saying is, if you have like 4 nodes in this network. This one is observable, so you see it, and then the question is like, is this node like independent of this? Or does there exist like an active path from here to here? So if a path is active, if each triple is active, so this is like A, C, and B, like A, C, and B, and then the last one is like a descendant of B. So what happens here is that these two are not independent because we observe this. So it's like knowing this, but changes our knowledge of this. Like, because if you imagine this as a practice example, you can have different possible causes of this thing. But this other thing could be a measurement of that. So effectively, they're like giving you the same. It's like, yeah, it's like, except the way I think of this is that this is some kind of measurement of that. So it's kind of like we know this, like this is like measurement of that. Like 1 or 2 minutes. So I guess another way to think about it is, you have to consider all undirected paths from like here to here. And if there is no active path, then there's no dependence. But in this case, there's an active path from here to here. By virtue of it, so there exists an active path. So we cannot claim that these are independent. Yeah. But it takes some time to think about. All right, everyone, I think we're good with the break, so hope everyone had a good break. All right, so let's get back into business here. So again, let's take a look at some of the examples here just to try to explain this a little more. So again, when we are looking at this slide, we are interested in the question of, are X and Y conditionally independent given some evidence variable? They are independent if they're de-separated. That means you consider all possible undirected paths to the two nodes. If there's no active path, they're independent. If there exists any active path, then you cannot claim that they're independent. They might be for some numbers in the table, but you can't guarantee that. We're looking for a guarantee here. So let's look at the one over here, the inactive triple. You have the first node, the second node, and the third one. The second one is your evidence variable. You observe it. Yeah. Because we observe that blocks the influence from the first node to the third node. And that's what I mean. This is like a single inactive segment. And in this, if this is the entire BaseNet, you only have 3 nodes. And there's only one path from this node to that one. And it's not active. So we're guaranteed that they're independent. We're guaranteed that this is independent of this, conditioned on that. That's the precise terminology. So whenever you see something shaded here, you have to think it's conditioned on that thing. For this, it's active. So this node and that node, if you have, if you are asking whether this node and this node are independent, conditioned on that, then the path is active. It's an active triple because you can go from here to here. So it's an active triple. In order for us to claim independence, we need no active path, but we just found one. So we cannot claim that it's independent. That means if we have this and this conditioned on that, then we cannot claim that there's independent there. But if we had this thing, then there's no active path from here to here. So that's why you can claim that this is independent of this. No conditioning here. So this is independent of this. It's like the example that we just saw. Yeah. X and Y are independent. Any questions on this? Yeah. Okay. So the question is, what does it mean for this arrow? Like it's squiggly instead of straight. So you could have more things in there. So let me write this. All right, you can have this, or you can have this, or you can have this. as long as one of these is shaded, that means you're conditioning on it, like that. So, yeah, so this is good. If you see this, then maybe let's do A and B, A and B. Are are A and B independent? Are they guaranteed to be independent? Yeah. So the answer is no. So it it's an active triple. So you need no active path to have independence. Yeah. But it's active. The intuition that I have is this is some kind of measurement of this. So if we know this, if we observe this, then we know something about this. So that means, yeah, we know something about this. So if we know this, it tells us something about that. Like this could cause that, or this could cause that. If it helps, another way to think about it is if you have this, it just reduces to this case. So, we're gonna go through some examples. Yeah, so with D separation, what you can do is, if you want to know that, the question is, if you want to know, are Xi and Xj guaranteed to be conditionally independent given some evidence variables, then check all the undirected paths between Xi and Xj. If there's any active path, it just has to be one, but if there's any active path, then the independence is not guaranteed. It might be true depending on how the numbers work out in your table, but they're not guaranteed to be true. So the whole point is to see if this is a guarantee. Yeah. So if all paths are inactive, then your independence is guaranteed. Yeah. All right, let's do some examples. So for each of these, I'll give you a couple of seconds to think about it, and then you can confirm if you got it. So is this guaranteed to be true? R independent of B? Uh, so yeah, they're guaranteed to be independent. So we're only asking if R and B are independent. So we're not conditioning on anything. Yeah, we got it. Condition on T. So by the way, so sometimes the back-to-back though, they might actually have the same thing. So it's not as if I give you another example, it's going to be different from the rest. So they might have some consecutive yeses and consecutive no. So just keep that in mind. Again, the question is when I show something, is this guaranteed to always be true from the structure of the Bayes net? Yeah, it's no, because this thing, like if you observe T, then that activates a path from R to B. And all you need is like one active path if not guaranteed to be independent. Yeah, so no. All right, what about this? L is conditionally independent of T prime given T. I'll give you a second to think about it. It's yes. Was that clear? So you have L, and then you have T prime. You have T here, it blocks the path from L to T. So this thing blocks the causal chain, and then this is guaranteed. All right. L independent of B. I see some different. So there's some disagreement, which is good for clarifying things. So yeah, they're guaranteed to be independent because you have L, then you have B, and then this thing is not a direct path. So you don't have a path from L to B because T blocks it. Because T is not observed. So it's not like, you know. Yeah. So this is no, because you have L and then you have B, and then the moment you observe T, it activates a path from L to B. So, yeah, question? So, so this one?
Yeah.
All right. So you have L, is that independent of T prime, given T? So what happened there, you have L, B, T, and T prime. That's a causal chain. You have like, it goes from 1, 2, 3, 4. And then the moment you observe one thing there, it blocks the path from any point in the chain. So I think the confusing thing here is that you also have B coming in. So it seemed like B is like part of it. So the way to think about this is, yeah. Just think of it like a path of 4 nodes. If you observe this, it blocks the influence from L to T prime. Now you have B here, but the only thing we're worried about is any directed path, any undirected path. Sorry, an undirected path from L to T prime. So this thing doesn't change the fact that we have a path here. So this is the only path that you could have that involves L and T prime anyway here. Yeah. Fine. L is L independent of B given T prime. No, because you have L and then you have B. This thing reduces to that B chain that you saw, like L and B here, but you observe T. Well, that means this gives you knowledge of T, which means you have L and B, then no, this is observed, so that means you know this. And so you have like a path, a undirected path between L and B. Yeah. So what about? Okay. Yeah, so this is guaranteed to be true because you have L, then you have B. This is observed, but this R is observed as well. So R blocks the influence from L to T. So because you have like anything that blocks the influence, it's not an active path. Yeah. So yeah, question?
Which one? The last one.
Yeah, so what happened there? All right, we have L, and you have B. So whenever we're analyzing independent, the only thing you want to do is look for undirected paths from L to B. So for that, what that means is just ignore D. D is like a distractor that we put in to make you worry about it, but it's not part of the path from, it's not, an undirected path from like L to B. You observe T and you observe R. Let me. All right. So I'm ignoring D because D is like a distractor that's designed to confuse you. So if our query is asking, is L independent of B? We need to find undirected path from L to B. Here's the only path. It's like it goes here, here, and here. It's like this is the only like undirected path. Now you look at T and R. So for T, you observe it. For R, you observe it. So you observe two things. All right, now this is a path of 4 nodes. This is the first triplet. And that's the second triplet. So you have, this triplet, then you have this one. The second one is active because T like sort of activates the influence, but the first one blocks it because you observe R. And the only thing that matters is if you have any single thing that blocks a path, then it becomes inactive. Yeah. So because there's no active path from L to B, that means it's guaranteed to be independent. If it's no, that means we had an active path from L to B. But this thing is blocking it. So I think if this is confusing, then the way to think about it is split it up into the triplet and then like go in a sequence. If it's easier, you can also think of it as, L R T B. Yeah, so this is undirected, but that's okay because for D separation, we're just looking at undirected paths. And then, it's like, I think it's easier just to think of it as this though, because R is blocking L from B, then no. This is the inactive thing, so it blocks the whole thing. Yeah. Yeah, question? All right. So the question is, what does it mean if something is observed? So what I mean for this is, if we're conditioning on something like conditioning on T and R, then that means we observe T and R. So if we're given something that means we condition on it, I guess observe means we know the exact value of the random variable. So you can think of L, B, T, and R as being like different bias like coin flips. And if something is observed, then that means you know the value it took upon. Like you might be given that, given the values of T and R, but L and B represent random variables that we don't know the value. They could take on whatever set of numbers is in their domain. Yeah. I know I'm recording all this, so if it's a little bit confusing, just go back to the video recording and then like replay this. No. Yeah. Oh, I see another question on the Google Doc. So can we conclude that if there's one inactive triple on the path, then the whole path is inactive, even if other triples are active? Yes. So I think I mentioned that here. Yeah. So you can have a path of that's very long. Here. Well, all right. So here's the chain. Like I couldn't write it out on one row because no, this is blocking it. But hopefully you see that there's arrows going from x1 to x2, then to x3, and so on. So if the question is there an active path from x1 to x7? If we don't observe anything, then there's it's active. But if I observe this, that means I condition on x5, then the whole thing is inactive because this thing is blocking. So like I try to go from here, then all right, so let's try another example. So you have four random variables: raining, traffic, roof drips. I guess that's why you need a D because there's already an R there. And I'm sad. Is T guaranteed to be independent of D? Given nothing, so we're not conditioning on anything, so there's nothing observed. By the way, it's also because we're going through a lot of examples. That's why for this, I'm not shading in anything, but just imagine that if we did condition on something, we really shade the node. Just that I'm not doing that. Like I'm not doing that for this slide, just because we're trying out many different things, so it'd be a little bit tricky to do that. Yeah. Well, I have people saying different things, which is good because that means we should discuss it. Yeah. I mean, if everyone says the same thing, I guess there's no point in having this discussion. So, all right. So the answer is no. So why is that true? Like why is this not guaranteed to be true? So I'll let you think about it. Yeah.
Because if there's traffic, there's higher chance it's raining, which guarantees a higher chance.
Yeah.
Yeah.
Well, yeah. So I think you're going through the different thing from intuition, but I think what I would recommend is trying to reduce this into the different triple that occur, and then you can kind of see what happens. So let's actually go back to the triple. So look at the inactive triple. So this thing is active. What this is saying is like we're not observing anything. So this is active, this is inactive. So what happened is like this is inactive. So if we didn't have R, then you could say that T is independent of D. But because we put in R, then there exists this path between T and D. So they cannot be guaranteed to be independent. Yeah. So again, my general suggestion is to think about this as splitting up the graph into the different triples. Yeah. Let me write it out. Oh. So we're conditioning on R. So we look at this. You have your path from T to D. This thing is blocking it. You have another path from T to D this way. But this is not observed, so it blocks it. Yeah, because both of the paths from T to D are blocked. So, yeah. What do you say? Oh, someone said yes. Um, so no. So the reason is, if you observe this now, then that activates the path here. So there's an active path. You cannot claim independence. Yeah. So it takes some time to think about this, but again, you can go through the slides and, this whole thing is being recorded. So just look back at the like 1 hour and 30-minute mark where we're at, and then you can think about that more. Fine. So given a Bayes structure, you can run the D-separation algorithm to build a complete list or a complete set, really, of all the conditional independencies that have to be true. Given that, graph structure, then you just write it out like this, xi is conditional independent of xj given as many evidence variables as you want, or as many observed variables as you want. So again, if you evidence and observation, like I'm treating them the same here. Yeah. And this list determines the set of probability distribution that can be represented. So we'll get to more of that soon. So if you look at these Bayes nets, if you look at the first one, if you see that Bayes net structure, then what are all the conditional independencies that are guaranteed from this, no matter what probability distribution you might try to make, given this Bayes net structure, given the assumption from it? But I'll give you a couple seconds to think about it. All right, so all the independencies from the first one, there's basically one thing. X is independent of Z given Y, because it's like Y is pointing to both Z and X. So if you're given Y and you observe it, that means you block the influence from like X to Z. And what about this one? You have X pointing to Y, pointing to Z. Yeah. That's the same thing as the first one, right? Yeah. So, yeah. Because again, the way that we drew the circle, it might be confused. It seems it might be confusing, but you just rewrite it so it's like X and Y and Z are like on the same line, and then you get your causal chain. What about the third one? Okay. Yeah, X is independent of Z. That's the assumption that is guaranteed to be true by any probability distribution following the Bayes-Nash structure. You might have other independencies that may turn out to be true, but they're not guaranteed by the structure of this network. So. Oh yeah, what about this one? All right, so why is it none? Well, so what I'm doing here is I took the joint and then I just did the chain rule. Probability of Z, probability of Y given Z, probability of X given Y and Z. But I can't make any more simplifying assumptions because, well, Z is already simple. Y depends on, Y has Z as a parent. So I can't remove Z. And for X here, X has Y and Z as parents, so I can't remove anything here. So this is like just the normal chain rule of probability. So it gives you no assumption. So a takeaway here is that the topology can limit the joint distribution that can be encoded with the Bayesian network. So again, the graph structure will guarantee certain conditional independency, but there might be more. Again, there might be more depending on how the numbers work out, but they're not guaranteed. And usually, if there's a lot more independency, then my argument is your Bayes net is not the right one for the task. You ideally want one that like encodes all your independency without, leaving the possibility of having many more like independencies. So let's look at this a bit. This is like your Venn diagram where each point is some probability distribution. So any point here is some distribution. And then you can think of like containment. So if a set is contained in another one, then like, so if you have something like this, a distribution in here is also in the bigger category. A distribution here is in the bigger category, but not part of this one. So. Yeah. So if you look at this, these are all the possible ways to have a Bayes net with like 3 random variables that make no independent assumption. So you cannot guarantee that there are any independency just from reading from the Bayes net. So that's why there's no assumption, and that's why this set is the biggest, because if you make fewer assumptions, you can encode more distribution. If you make more assumptions, you can encode fewer distribution. Like more assumption means you have a stronger like stronger set of assumptions in some sense. So that's why if you have full independence, like this is like the maximum amount of independency that you can have. X, Y, and Z, they're like no arrows connecting them. So that means they encode like the maximum amount of possible independencies. And then that's why they're a subset of the full thing. Yeah. Any questions on this? So again, just think of this as like your Venn diagram that show like every point in this is like one probability distribution over 3 random variables. 3 because we have X, Y, and Z here. So all right, some more examples. So if you consider this 4-node Bayes net, then the way to compute the conditional independency are as follows. So again, it just for every node, you just condition it on its parent, and then you can make the joint like this. So if you want to know what is this, then you can apply your normal chain rule, and then you get rid of in the conditioning anything that's not apparent. So we wrote out the full step, but just think of this as like, following multiple steps of the chain rule. So this is again just the normal chain rule of probability, and then you remove for each node, stuff that's not apparent when you're conditioning. Yeah. So here's another example. So this will be the last Bayes net example that we'll go through today. I think you're probably tired of looking at all these examples. So you have a Bayes net where battery off, light off, and no motion. So these are some numbers. So again, we're just going to assume that we give you the table. Then you have your numbers here. So what is the probability of plus m? So it's somewhat confusing that. So these are like things like battery off, light off, and no motion. But if you say plus b, that means battery off. Then the example might be a little bit confusing, but just think of it as like plus b and minus b, and instead of like thinking about battery, light, and no motion. Yeah. So the way to compute that is here's how I would do it. You have your single random variable here. If like observed, and this goes back to the other question about what does it mean to be observed. So we are observing plus m, but b and l are not observed. That means we have to go through and enumerate over all possible values of b and l. Now, b and l, the only possibilities are plus and minus for each, so it's a simple example, but in theory, you could have maybe dozens or hundreds of millions of values of b that you have to sum over. So this is the normal formula for marginalization. This is what happens when you factorize it using the chain rule, and then you remove the parent and the conditioning. What's going on here is that you can pull out anything that doesn't depend on L out of the sum. So this is like how you do like algebra with different sums over things. It's like another way to think about it is take your sum over L and then push it as far right as you can until you hit something with L in it. And if you're lucky, then you get the sum over P of L given B, and then this is just a probability distribution. It has the sum to 1. So that means it goes away, and then you get something like this. And these two lines are just going through like the different cases of plus B and minus B. Yeah. So hopefully that's all okay. If If not, then just go back to the slides and the video, then you can go through it in your own time. Probability of plus L. Yeah. I'll give you a couple seconds to think about it. Or at least you can get you don't have to get like the final number there, you can just like get, I think the more important point is you get the algebra and then you get to like the last step before you substitute things in. Like, I feel like that's the more important thing. Um, so yeah, this is what I did. So it's basically similar to the last slide, except we now observe plus L. That means we have to sum over values of B and M. So that's why here we write plus L, because that's the value that we observe. But B and M are not observed, so we have to sum over all their possible instantiation. Which in this case, again, is plus and minus, but you can imagine they might have like 10 value, 20 value to sum over. And we're applying the same rule of pushing the sums as far right as possible. This one, so you see that the text is bigger, so you see that the algebra is probably simpler because otherwise they couldn't have fit it in the slide. Yeah. So do you remember Bayes' rule from before? Yeah, I just gave you the how to solve it. So yeah. So yeah, this is how you do something like it. You get probability of this thing, which is from Bayes' rule. You just flip the you saw the formula from a few classes ago. So like this is how you do it. Then you plug in the numbers, and yeah, you should get something like this. Now this one is a little bit more interesting. So just for the sake of time, let me just go through how it is. Then you can always review it as well. So what I did here is a probability of plus M conditioned on plus L. So here I didn't do a sum over B. I just wrote out like plus B and minus B. So before I was writing a sum, here you just have the value of plus B and minus B. This is just a way of like writing out the sum, which would marginalize our B. And from here you can apply the chain rule, then apply the knowledge of the Bayes net to remove the parents of the node, and then you plug in the number. So, yeah. So to summarize, so yeah, Bayes nets compactly encode joint distributions, and from looking at them, you can guarantee certain independency. There might be more, but there's at least a few that you can guarantee based on the structure of the Bayes net. And you can use the D-separation algorithm. Maybe, I mean, in practice, you would implement it on a machine, but if you're just doing it by hand, you can just see how it works. And yeah, again, the Bayes net joint distribution might have further conditional independency, but D-separation will give you what's guaranteed. Yeah, so to summarize, so we reviewed Bayesian networks today, as well as we had Bayesian networks Monday as well. We talked about conditional independence assumption, how to answer queries. And next class, we will talk about Bayesian filters, which are things that you might have expected use Bayes net as part of their assumption for this one. So yeah, I will see you Monday then.